Breaking down escrow.scrypt. So the first thing I'd like to note is that it's easier to think about this in the context of using both escrow.js and escrow.scrypt at the same time, because escrow.js is going to be the actual deployment, which will give us all the parameters that we need to interact with escrow.scrypt to unlock it and lock it. So the escrow.js can be found in the deployments folder of the boilerplate, and escrow.scrypt can be found in the contracts folder. A couple things about escrypt. There's static typing. So if you never used this before, it'll be a bit new, but you have a couple different types of variables that you can have. Integers are handy if you want to compare size of numbers. Bytes can be any arbitrary message if you want to like check equivalence of a message or use a message. Then you can be looking at bytes, and you can just use like a buffer to convert a string into bytes. And then Boolean is true and false, which can be helpful for conditional statements. And then RIPEMD160 is the hashing function used for Bitcoin addresses. And then SHA-256 is a hashing algorithm which is used for Bitcoin transaction IDs. And then we have util.scrypt, which you can import into your contract. And this has some helper functions so that you can access some of these functionalities without knowing exactly how they all work, which is pretty handy. And then you have helper.js, which is the helper functions for escrow.js. This is like when we want to load the assembly language version of your contract, like right here. This is defined in the helper function. See? So, the first thing I would start in escrow.js actually. And the first goal will be to get all of the variables which we need to make the locking transaction. So the first thing we need is public key hash A, and to get that we'll just use BSV library to create a new private key from random from the testnet because we're using testnet. Then we will get the public key from it, and then we'll just run SHA-256 RIPEMD160 out of the crypto library of BSV. So that gives us public key hash A, which is just an address really. And then we have public key hash B, which is the same thing from a different randomly generated BSV private key. And then we would do the same thing for public key hash E. So these are Alice, Bob, and the escrow agent. And then hash secret 1, simply going to use this string and create a buffer, and then we'll just use a SHA-256 on it. And then we'll do the same thing for hash secret 2, and then fee, which is just large enough to cover our fee. So once we have all those variables, we can actually create a new escrow of it, which is using the assembly language version of escrow.scrypt, this gets compiled into an assembly language version, and that's how we can actually use it in our transaction. So it passes in these variables, and you'll see that these are actually in the order of the variables over here. And so all this really does is create a script, which is a This is a BSV transaction in the JSON version, and the script is actually just going to be like right here. So all we're really doing is creating a script, a much longer version than this, and putting it in one of the VNs. So const locking tx equals await create transaction. Okay, so we're just making a very basic transaction right here and just adding in an address, an amount, and a fee. So we're just getting this started. But once we actually create an output and set the script to the escrow.locking script. So escrow is an object here created by this contract class. We'll set the script of the first output equal to escrow.locking script. So output v0, v out is the output, v in is the input, and we'll just set the script to the locking script. And then we'll use the sign function create locking tx, which is in here. So one of the helper functions was create locking transaction, and it has a helper function of sign. So all we have to do is run sign private key. That will make a valid transaction that we can actually broadcast. So we have basically a transaction just like this at this point, and then we can broadcast it by using sendTX, which is also from the helper functions. We now have a fully locked transaction holding some Satoshis, and it's ready to get unlocked. So right here, you would probably break this in half, and like in your application, you would have, okay, function A, Alice and Bob make the escrow, and then later we're going to actually unlock it. So this at some point later in time, we'll come back to this and regenerate starting here. So now it's later in your application. For whatever reason, we're ready to unlock this escrow. The first thing we do is we get the previous locking script, which would just be passing in these same variables which you used to initialize escrow the first time, and getting that locking script to assembly language. And now we're going to get ready to unlock it. So what we're aiming for here is we're going to try to use this unlocking function, which we have defined in this script. We need a bunch of variables before we can even talk about unlocking this. So let's try to generate those variables. The first thing we'll do is create a brand new BSV transaction, which is totally empty. And that's going to be our unlocking TX. And then the first thing we'll do is add an input stating the locking transaction and input index, which is equal to 0. So this is just telling it where to look in the outputs. And then script, which is just going to be an empty script at this moment, but we're about to fill it in based on these different scenarios which we can use. So we'll get right back to that one second. And then we'll use the locking script, which we regenerated because we had all these variables when we want to unlock it, and amount, which is, I think, arbitrary, yeah. So this is got to be the same amount that you used when you created it, so that you can actually pay out the escrow, but okay. So we have a couple of different scenarios here based on whether Alice and Bob are going to be paying each other or if they're just going to split it. So this switch scenario thing, so here we just have scenario hard-coded to 1, so let's just go on that premise here. So in case of 1, we're going to create an output So this is just adding a basic VSV output transaction. So we're going to send some Satoshis to the address of private key A, which is Alice. And we're going to set the Satoshis equal to the amount divided by 2 because we're going to be splitting it, and then minus the fee so we don't run out of Satoshis here. And then we'll do the same thing for Bob. So private key B, which is Bob, and make sure his Satoshis are set there. And then we'll set the fee to the remainder of what's left. So if we're going to split it, if we're going to give it to Alice, then we'll use case 2. It'll send all of the Satoshis minus the fee one time to Alice's public key address. And then case 3 would be sending all of the Satoshis to Bob's address, which is right here. Depending on the scenario, we will move forward. And the next thing we'll do is get the pre-image of unlocking TX, previous locking script, and amount. So what pre-image is something that we can look at within the script contract. It is specifically, it's the inputs and outputs hashed. So this is how we can actually examine what a transaction is in order to unlock it. So if we're going to split the transaction, we have to have both Alice and Bob's signature so that if it was going to go in Bob's favor, Alice couldn't simply sign it and then split the funds and get off scot-free, basically. So if they both agree to split it, then it's pretty obvious that they both deserve it. So we'll get a signed transaction using Alice's private key, and it'll just be the unlocking transaction plus that locking script to assembly language again and the amount. And then we'll also get the same thing from Bob. And then we will actually create this unlocking script. So we're gonna call the unlock function from that escrow class. So back when we created escrow up here, we recreated it now that we're unlocking it, and we are calling that unlock function. So here, in order to actually spend it, status has to be true. Otherwise, this whole thing is meant to break. So that's why status is false until status becomes true here. So if we pass all these variables and they pass all the tests within this function, then it'll actually go ahead and spend. So first thing we need is that sighash preimage. So this is the hashed inputs and outputs, and we pass that in as number 1. Then we need the public key of Alice, as you can see here. So we need preimage, public key 1, signature 1, so we need Alice's signature next, which is what we get. And then we need Bob's public key and signature, Bob's public key and signature, and then secret bytes. So if they're splitting it, I guess we don't actually need to have the secret phrase. So you'll see that if we're actually going to be splitting it, because if we get both Alice's and Bob's pub key hash, then we don't actually have to get to the secret at any point. So that's why secret can actually just be empty there. In case 1, which is what we're running on right now, we are making those variables to the script, and then we go ahead and set the unlocking transaction inputs to that script, and then we go ahead and broadcast it. So now that we broadcasted it, it's going to try to unlock. Because it's on scenario 1, it got Alice's pub key equal to pub key hash A, and it also got pub key hash B, which is Bob. So then it'll go ahead and try to split. Use the split function, which is defined up here. So in that case, we need the amount and the tx pre-image. So then it'll actually create a spend output to Alice's address, and then it'll create a spend output to Bob's address with the correct fees and amounts. Same amount, and that has to be the same amount that we made here, because if it's not, then it's going to fail the equivalency of the pre-image equal to the output, which we're about to see here. So we're creating this outputs bytes, which is equal to the spend address to Alice and spend address to Bob, and then that has to be equal to the hashed output of the tx pre-image. So that's why it has to be the same as we passed in right here, in the hashed version, right? Pre-image. See, we hashed that pre-image here. So if it's the same as that, and then it's actually going to return the equivalency, which would be true. So if split returns true, then it require will be fine, and if it's not true, it'll be false, in which case require will fail. So if require fails, then basically this whole transaction will not execute. So that is scenario 1. Now scenario 2, if we have only Alice's signature and we have the escrow signature, then when we pass this in, we have to have the actual secret buff 1, and you're about to see why in a second. So if we're on scenario 2, we're going to have Alice's and escrow public key hashes. So that means if pub key is equal to Alice, this will be yes. And then if public key hash 2 is equal to Bob, and this will be no. So then we'll go down to here. And if public key hash 2 is equal to escrow, that will be yes. So we're going to be in here. We need the secret here to be equal to the hash, which we declared back when we first created the thing. So this is basically the escrow's password. So if the escrow has the correct password and the escrow gives a signature, then we're going to actually override Bob's absence and give it to Alice. And that's, at this point, it's going to use the spend function. So here we're checking if the pre-image only has an output for this specific address. So in this case, we want to make sure that the output has a spending output for Alice. And if it does, it'll return true here. If we create this output transaction, then with Alice's public key and the correct script and the amount and the fee correctly, then it'll actually return true, in which case we can actually go ahead and spend. So that'll set. At that point, we've verified that the secret is correct, and we've verified that the pre-image is equal to spending to Alice. And then will be status is true, and then it'll go ahead and spend. And then lastly, if we're talking about, we have Bob's signature and the escrow signature, then we'll be going down to here. It'll go if escrow public key 1 equals public key hash A, and this will be false. So now we're down to here. And if it's Bob and the second one is escrow, then we're looking to see if the secret password 2 which is only known by escrow, is equal to the secret, which we hashed earlier. So here's the secret, and then we want to make sure that's equal to hash2, which we declared way back in the day. And then we will use the spend function again to check if the pre-image is going to allow us to spend to Bob. So we want to make sure that this is true and the amount is equal to the correct amount, and the pre-image is the transaction which we're dealing with here is equal to, and this has already been required to be equal to the transaction which we're currently inside. So this is what we call the op push tx, which is like a key breakthrough of escrypt. So in this case, if the transaction is set to spend to Bob and is the correct amount, then we'll allow it to execute. And just to show you that it works, I will be in the deployments folder here, and I'll run node escrow.js, and it created the funding transaction ID all the way up here, and then it went through all of these other steps for case 1 because that's what's active right now. And split it between Alice and Bob. And if we look at this unlocking transaction, and here we go into the test what's on chain.com, we can pull up that transaction. And we see that it spent to these 2 addresses. Now if we go back and change it to scenario 2, so remember these addresses, N4M and MZ9. And we look at this unlocking transaction. Should only be one of these guys gets the money. Well, since we're getting a random one each time, because you see we're not reusing the addresses, it's spent to the random guy, but that's the desired result here. So, and then the same thing would happen if I switched it to 3, which I'll just go ahead and do. And this again, you'll see only one person got the money here. There you go. That was a lot of information. Hopefully you've learned something about the SIGHASH pre-image, which is basically the secret sauce of escrypt, and it allows you to check if the conditions within the transaction are being met before it can spend itself. So once you get that, then you can do all kinds of cool stuff. So hopefully in the next one we will get into Rabin signatures, which will allow you to actually use external events to unlock different conditionals within your script. So thanks for watching, and see you in the next one.